All right, we're continuing our discussion of the postulates of quantum mechanics. In the previous videos, we introduced the wave function, and then we talked about the Born interpretation, which tells us that the square modulus of the wave function is related to the probability. Excuse me. And these two postulates produce some important criteria for wave functions. Part of this is just a mathematical anomaly. If you solve the Schrodinger equation, there's multiple possible mathematical solutions, and they don't all necessarily work. But part of it is based on sort of physical meaning, and I wanted to discuss that. So there are 4 criteria for an acceptable wave function. And there's far and away one of these which is most important. That's the first one. So wave functions must be square integrable, right, or normalizable. And I want to talk briefly about what that means. So imagine I had some wave function which looked like this. Here's my wave function. It's a function of x. Oh man, right. Imagine it looked like that. A specific mathematical form might be something like this. Psi equals n sine x. Right? So this is one hump of a sine function. This n up here is just some constant. And it will turn out that if I adjust n, you adjust the amplitude of that curve. So if n gets bigger, oh, that's an awful sketch. It goes like this. If n gets smaller, the amplitude gets smaller. N does not change the shape of the curve, right? It just changes its height. Well, I know that the square of the wave function is related to probability, right? So again, if I were to go and plot the square of the wave function, or really the square modulus. So this is now psi squared versus x. It would look something like this. If I adjust n, again, the shape doesn't change. The only thing that changes is the height of this, so it would get bigger or smaller. And I know that this is related to the probability, right? Specifically, if I integrate all of this area, I have to get 1. And so at this point, what we need to do is adjust n so that the total probability, if I integrate over all space, is equal to 1. Okay, that is, again, p equals psi star psi d tau. If I have a wave function which looks like this, a normalization constant times psi, if I integrate over all possible values, which I'm just going to call all space, I get n psi star n psi dx in this case. Right? This is a math problem, right? And it will allow me to calculate n, figure out what n is. So this process of adjusting the height so that when you integrate over all space, you get a probability equal to 1 is called normalizing the wave function, right? Or determining the normalization constant. So this n is formally called the normalization constant. See the worksheet problem. It'll be a good one to do and will be helpful to you. So let me quickly run through these. The criteria for an acceptable wave function: it must be square integrable. If the wave function looked like this, you know, psi versus x, right? This wouldn't work. The particle's got to be someplace. If it blows up and I can't normalize it, it doesn't work. The wave function must be single valued. So if I had psi versus x, which looked like this, this doesn't work. Right? And the reason is that multiple probabilities don't make physical sense. Right? It can't be 25% and 50% and 75%. There has to be one unique probability for finding it. The wave function must be continuous. So if I had a function which somehow looked like this, that doesn't work. And the reason is that the physical behavior of the wave function has to make sense. It can't be 50% here and then 75% here. It has to be continuous and smooth. Last but not least, right, the wave function, the slope of the wave function, the first derivative, must be continuous. So if I had a function that looked like this, where there is a discontinuous slope, right? Here it's positive, here it's negative. This doesn't work. The reason is, as we'll see here in a little bit, some properties are related to the slope, and these must also be well behaved. So there's this famous saying about quantum mechanics, which is that quantum mechanics is weird, but it's not kinky, right? No kinks in quantum mechanics. All right, I will stop there, and we'll move on to the other postulates in the next video.